Okay, so since the amplitude of a wave gives the intensity when you square it, again we associate this quantity phi that I've written with the amplitude of the particle wave. So again, we recognize now that quantum particles, photons, electrons, some others, have both particle-like and wave-like characteristics, and now we associate this quantity phi, which when you square it gives the probability of finding that particle at a particular position. We associate that quantity phi as with we identify it with the probability amplitude of, or the amplitude of the particle wave that is associated with that particle. Okay, and since it's an amplitude and since it's a wave, basically you have to sum the amplitudes first and then square them in order to get the probability. So for example, P12, the probability of finding an electron in the electron double slit experiment when both slits are open is equal to the amplitude of the two particle waves, electron waves, that you would have if you closed slit 2, so you'd only have slit 1 open and only slit 2 open, phi 1 and phi 2. You have to sum these amplitudes first and then square it in order to get the probability. And this is again another fundamental thing that we do over and over again in quantum mechanics and any sort of wave mechanics, is that you have to, interference comes from the fact that you sum amplitudes first and then square to get intensities or probabilities. Okay, because then you allow for the possibility of waves being out of phase with respect to each other. If you square first, then the phase dependence goes away, because you basically average over time a squared cosine function and you get just a number. All right. Oh, I should say what's shown over here on the right is actually the results of an experiment with electrons, which is very difficult to do. Basically something which is very close to a double slit experiment for electrons, and where basically these different numbers here that I've indicated, 10, 200, 6,000, 40,000, 140,000, this is the total number of electrons which have hit the screen, hit the detector. And so you can see that the detector actually can register individual electrons hitting it. Okay, this is now a different kind of detector that is more like a camera. Okay, so it measures a whole area, and then if you only have a few electrons, you don't really see any obvious pattern. But then as we let the experiment run longer and longer and we accumulate more and more electrons, we start to see a pattern emerging, and eventually it looks exactly like you would expect from a double slit experiment, where you have waves of a particular wavelength that are given by the energy of these electrons. Okay, and so you see these interference fringes, even though we know that we're detecting individual particles, because we can see the individual particles hitting. We can see the results of them hitting the screen at particular places, but yet we still get this interference pattern. So this is to tie it all together. This is the actual results of a real experiment. Okay. Now I just want to make, in closing, a note about quantum particles. If we can accept or learn to accept the notion that waves and the particles, the quantum particles, display both wave-like and particle-like attributes for electrons and photons, for what we've been calling quantum particles, then we have to ask the question, then what distinguishes them from normal particles? So why when we did the double slit experiment for the bullets, why did this experiment not show interference? Why did we see just a normal sort of particle-like probability distribution when we opened both slits? And the reason is that in fact there is a interference pattern, but it turns out the wavelength for normal particles, that is larger particles, is so small that these wiggles basically get averaged out.